In 1998, two PhD students, Brin and Page from Stanford University, had a question. Of all the pages on the internet, which one matters the most? And the way they have defined this importance is one of the most elegant ideas in the history of applied mathematics. Imagine a person sitting at a computer with endless amount of time. They open any web page at random, then click on a link inside that page, then click on a link inside that page. They do not search for anything, do not enter anything on the search bar, just keep following random links through the web pages. The question is, in the long run, what fraction of time does this random surfer spend on each web page? Now this random walk is exactly a Markov chain where each web page is a state and the surfer is always in exactly one state. The transition probability from page I to page J is simple. If page I has k outgoing links, each link is followed with probability 1 over k. If there is no link from I to J, the probability is 0, and this gives us the transition matrix for the internet. And the stationary distribution of this Markov chain is what we call as the page rank vector, where the entries tell us the page's importance score. But this is not as easy as it sounds. In the internet, you might have some web pages with dead ends, no outgoing links, the random surfer is stuck there. Brin and Page solved these problems with something they called as a damping factor. So in the model they made, they assumed that there is a 85% chance that the random surfer keeps following the same links, and there is a 15% chance they jump to a completely new link on the internet. Now introducing this damping factor of 0.85 handles two things. Number one, it handles the dead ends. Number two, and very important, is that it ensures that the matrix satisfies the requirements of Perron-Frobenius theorem, which ensures the existence of the stationary distribution. So, the rank of a web page is the stationary distribution of the Markov chain on the web graph with some damping factor. Now, we know from a few reels back that this stationary distribution satisfies this equation, but what does this equation exactly look like for page rank? An even more important and interesting question is, how did Brin and Page compute it for such a big matrix? And that's for the next reel. Follow and save this one, as math only makes sense in order.